Today, we are going to discuss the quality of experience parameters which need to be traded off. Some of these parameters are of utmost importance, whereas others could be bargained in lieu of the former ones. In this module, we shall formally describe what is trade-off, why is it necessary, how do we make the trade-off. Then we are going to see some real-world scenarios in communication links and networks. Looking at all these quality of experience parameters, we agree that we need a holistic solution that takes care of all of them as a fine balance. We call that as a holistic solution. Formally speaking, trade-off implies to bring a balance between the desirable and incompatible parameters such that a compromise is achieved between all of them. It is so because some of the quality of experience parameters often have conflicting goals and implementations. For example, if we look at availability versus affordability, if we want to achieve 5 nines availability, the affordability would become low because we'll have to invest a lot in order to gain 5 nines availability. Likewise, another interesting relationship exists between usability versus security. Systems that are overly secure tend to become less popular and usable amongst the end users. Let's look at a simple communication link trade-off. In order to achieve communication efficiency, we implement compression. Let's say we are looking at an image processing and image transmission scenario. So with a compressed image, we are getting reduced transmission time and reduced communication costs. However, it is being achieved at the cost of increased CPU time because the compression takes computational cycles. So we need a trade-off between computation and communication. At the network level, this figure shows you a trade-off that exists between throughput and fairness. If you look at these nodes which are willing to transmit to each other, if A is transmitting to A complement, B to B complement, C to C complement, and X to X complement, looking at the given scenario, if we want to achieve throughput, we would rather allow A, B, and C to transmit and bar X from transmission. In this way, the communication channel would not have any conflicts and contention. But this is in direct confrontation with the goal of fairness. So we need to actually strike at a balance between throughput and fairness. How could we achieve that? We could achieve that by possibly allowing schedules, more weighted schedules to A, B, and C, and less weighted schedule to X. This way, we could find the balance between throughput and fairness which the network users would accept. Design trade-off is more like a knapsack problem. What is a knapsack problem? You can think of it as a child with a 100 rupees note that goes to a convenience store. Looking at the psychology of a child, you can well imagine that the child would like to buy ice cream, chocolate, chips, and other things. But can he afford that in 100 rupees? He'd have to think about a compromise or a trade-off in order to achieve his desirable things. Specifically speaking, if we look at it as a bag that cannot allow more than 15 kilograms of weight, and given these boxes, each with a weight and a price tag associated with it, if we were to achieve a weight that does not exceed more than 15 kilograms of weight, while giving the maximum value in terms of dollars, we can come up with a mathematical formulation. That is, we can think of maximizing this expression, that is V sub I, X sub I, where V is the value of the item I, and X is the weight of the value I. It is subject to the constraint that the weight cannot exceed the upper bound. If this is so, it becomes a knapsack problem or a child with a $100 bill. In terms of networks, the same can be translated because we have seen these desirable features such as scalability, availability, performance, and all these. If all of these were to add up to 100, we may have to think about it. How much importance are we going to give to security, reliability, affordability, etc.? This again can be taken as a knapsack problem in which we want to maximize the overall utility and usefulness of a network with all these desirable features while respecting an upper bound of 100.